Hi everyone, my name is Nam. I'm a PhD student at the University of Adelaide. Today, on behalf of my co-authors, I would like to present our work on the optimal sizing and scheduling of community battery storage within the local market. So I will first start with the background on the problem that we want to discuss today. As you might know, the electricity network has been getting greener in the past couple of years due to the increase in rooftop solar PVs and residential battery capacity storage. And as a matter of fact, there is now a decrease in the total consumption from the grid as it is replaced by rooftop PV's generation. And this also means a reduction in the revenue of the electricity retailers because they have reduced sales compared to the past. Moreover, the uptake of distributed energy resources creates a challenge for the service providers on a daily basis due to the great amount of reverse power flow during the middle of the day. And in order to manage it, many regions have introduced the export limit for solar customers, and they're not happy about that. So in conclusion, the uptake of residential PV systems not only affects the electricity retailer, but also the system operator and normal customers. Although the negative impact is inevitable, but getting to understand the future, there's the opportunities to resolve the mentioned issues. Therefore, our motivation is to propose a solution to resolve the issues for electricity retailers and indirectly help the system operators and rooftop PV owners. So this brings us to our research proposal. So the solution is to propose a local market that facilitates energy transaction within the community of consumers. In this respect, retailers can offer a trading platform to the local communities and directly participate in the market as an aggregator, which then directly interact with the solar customers. And the reason is that normal customers that is equipped with these solar PVs along with the automation and behind-the-meter solar systems are becoming more flexible. And this is good news because it means that the collective flexibility can be aggregated to create a new business opportunity for both the retailers and prosumers. In addition, the aggregator can install and operate a large community-level battery storage for the local market to assist the energy sharing process by filling the gaps in the local energy production and demand. And most importantly, it increases the revenue of the aggregator. And we will show this in more details in later slides. So if we look at the literature in terms of the local market structure and how to operate it, it requires an understanding of local consumers. Specifically, we are looking at the modeling of load flexibility and price responsiveness of the electricity consumers. However, most of the papers only focus on a single interval market operation by ignoring the time coupling nature of shiftable load, which is the load rebound effect. So what that means is that if we decrease the consumption in the current interval, we must consume more with the exact value in later time steps, and this is not considered in many papers. So next, the problem requires an understanding of the business models. However, there's still a limited business model for the aggregator to make profit, and also the current state of the art still lacks a simulation platform to test these different models. So in terms of battery sizing, although the problem has gained significant interest, most of the works are limited to a single household or aim to meet the anticipated consumption at a minimum storage capacity and not considering the impact of the prosumer's response. So therefore, with the aim of concerning the prosumer's response and developing a sustainable business model for the aggregator, the problem requires a game theory concept. So in this research, our ultimate goal is to investigate two business models for the aggregator in a local market setup that is equipped with optimal community battery storage while considering prosumer responsiveness and available flexibility. So for our research methodology, we want to consider a stackable game-based approach for operating the local market and sizing the community battery. And because the aggregator operates the local market as a centralized entity, the aggregator is proposed as the leading player. The objective of the aggregator is to maximize profit by determining the local prices as well as the sizing and operation of the battery. And the followers are prosumers, who are considered rational via the administration of a home energy management system. Similarly, the prosumers also want to maximize their utility by adjusting the consumption with respect to their available flexibility. So as you can see, because both the aggregator and local prosumers want to maximize their interest, the problem is regarded as an instance of stackable game, which can be formulated as a bi-level program. So in this model, the local buying and selling prices from the upper level problem is passed to the lower level. Thus, they are regarded as distant variables for the leader, while being considered as non-parameters for the followers. And conversely, in the lower level, each prosumer maximizes their interest by optimizing the consumption and pass the information back to the upper level. As I mentioned before, the optimization problem of the aggregator is to determine the local electricity prices and battery operation in an attempt to maximize profit. Then its objective function consists of three main parts. The first one is the interaction with local prosumers. And the second one is the interaction with the electricity retailer, because the aggregator is regarded as a middleman between the retailer and the participating prosumers. And lastly, the objective function requires a minimization on the battery operation by considering a per unit cost on the amount of energy discharged from the battery. And this aggregator has 5 constraints. So the first one is to ensure that the local market always provides more incentives than the conventional retailer. And this means that the local selling prices must always be higher than the selling prices from the retailer, or in other words, the feed-in tariff. And the local buying prices must always be lower than the electricity charges from the retailer. For the second constraint denotes the local net demand from the aggregated energy profiles of only prosumers and the battery operation. And for the third constraint, we are looking at the battery state of charge determination at every time interval, with the lower and upper bounds in constraint number 4. Finally, the limits on charging and discharging power are presented in the last constraints. And for the local prosumers, after receiving the prices set by the aggregator, they can vary the consumption to maximize their utility. The prosumer's utility is a combination of electricity payment and usage satisfaction. So the idea is that if they increase their demand, the satisfaction level is increased at the expense of the higher electricity bill. And conversely, if they consume less, the satisfaction level decreases, as well as their electricity bill. And this counter effect between the two terms leads to an optimization problem for the prosumers. So in this problem, the lower level has 2 main constraints. So firstly, depends on the prices, prosumers can vary their consumption either upwards or downwards to minimize their cost, with the batteries to be specified in the first constraint. And secondly, since most of the household appliances are shiftable loads, meaning that there is a rebound effect for most of the considered flexibility, therefore at the end of the time horizon, the adjusted consumption must always be equal to the expected demand, as represented by the second constraint. Overall, the whole bi-level problem can be solved by deriving the KKT optimality conditions for the lower level problem, which turns the optimization problem into a single level model. However, this conversion introduces new complementarity constraints and combines only the decision variables from both levels. So if you look back at the lower level model, after converting into a single level model, both the price B and the consumption X are decision variables, causing the first term in the objective function to be a bilinear term, making the whole problem to be non-convex. Or in other words, it is not easy to solve within real time. So in order to address the issue, we proposed a workflow for solving this bi-level model. In the first step, we apply piecewise linear approximation on the lower level problem, as shown in the figure, where the blue line is the usage satisfaction as mentioned earlier, and the orange line is the piecewise linear approximation of the blue line. And then in the second step, we apply a strong duality theorem on the lower level problem to obtain the equivalent linear expressions for the product between the price and the consumption. And lastly, we substitute the lower level problem by KKT optimality conditions to cast the bi-level program into a single level model. And if you need more details on the formulation, it's in the paper. So now we move on to the case study we've run. So for the simulation setup, the simulation is performed on 33 prosumers in Sydney, Australia for 36 days. Specifically, the first 3 days of each month were selected, in which 2 days are working weekdays, and the third day is either Saturday or Sunday. For the electricity retail prices, we use Energy Australia, which is one of the largest electricity retailers in Australia, as references. And since the aggregator is considered as a commercial company, they are exposed to business retail prices as shown in the figure on the right. And the business tariff has different prices compared to the residential plans as shown in the left figure. One important key to remember before going into the results is that if you pay attention to the business tariff, there's no peak price during spring and autumn months. So the highest tariff during these months are only about 30 cents per kilowatt hour. This peak price is also not available for every weekend throughout the whole year. And this slide shows the flowcharts for the proposed battery sizing model, which consists of two main parts. So firstly, as mentioned before, we want to investigate two business models in this research, and that is done by considering two different pricing schemes. And here, we call it one price scheme and two price scheme. The one price scheme means that there is one consensus price within the local community such that buying and selling prices are equal. Whereas for the two price scheme, the buying prices are usually higher than the selling prices so that the aggregator can make more profit. Next is the battery sizing model. And since the horizon of this problem is 24 hours ahead, so typically the sizing duration is limited to 1 day. Although the problem can be optimized for multiple days, the computational time grows exponentially with respect to the number of discrete intervals. And in this regard, we run the optimization problem for each day to obtain different possible battery sizes and consider them as candidates to find a single optimal capacity for the entire 36 days. And in the problem, we assume that this community battery is constructed by stacking multiple Tesla Powerwalls together. And here are the results that we've got for running the optimization problem for each day separately. So the green and blue bars are going to be the weekdays, and the orange bar is the weekend. So for these two figures, which represents the aggregator profits, what we can see from them is two things. One is the aggregator is always profitable in either of the schemes, although in some months, the profit can be negative due to different price structures from the retailer. And second, we can see that the aggregator can receive higher payoff in the two price scheme than the single price scheme because when there's a gap between the two prices, the aggregator can buy the energy from the prosumers at lower prices and then sell them back to the consumers at much higher prices. And in terms of battery capacity, as you can see, there's no orange bar in any of the months and no bars in April, May, September and October, which represents zero value for battery capacity. So the reason is because the battery operation is only economical during peak price intervals, which is due to the high price of the battery. And if you remember from the reference retail prices, these peak price intervals are only available during weekdays and in some specific months. Therefore, the results show that the optimal result is to not have any battery during those periods. Also, from the battery capacity, we can see that during the winter months, which starts from June to August in Australia, the results show that the capacity should be higher than the summer months. And this is because days are longer in summer, prosumers can generate more electricity from the rooftop PV systems in the early morning and late afternoon when they need energy the most. And therefore, less energy is imported during peak hours, which results in a smaller battery size compared to the winter months. So upon obtaining the optimal battery size for each day, the values are then used to find a single optimal capacity for the entire 36 days. And again, we assume that this community battery is constructed by stacking multiple Tesla Powerwalls together. So the figure here shows the net profit from different numbers of Powerwalls for both pricing schemes. The results show that the ideal community storage is 6 Powerwalls for the two price scheme, which is equivalent to 81 kWh and 30 kW power rating. Whereas for the one price scheme, the optimal solution is 7 Powerwalls, which is equivalent to 91.5 kWh and 35 kW power rating. However, since the difference between the profit of 6 and 7 battery units in the one price scheme is minimal, we decided to use 6 Tesla Powerwalls at the optimal result. In this table, summarize the aggregated profits for 6 Tesla Powerwalls in both pricing schemes. And considering the cost of the battery, the payback period is roughly 5 years and 9 years for the 2 price and 1 price scheme respectively. So what this means is that the aggregator can totally recoup their cost and make profit within the battery lifetime, which is usually at least 10 years. So with 6 Tesla Powerwalls, 1 Weekday in December, which is the summer in Australia, I used to highlight the prosumer demand response and community battery operation. So from the first graph, the orange line represents the original net demand and the blue line represents the adjusted net energy time series. Whereas in the second graph, the orange line represents the battery state of charge and the blue line represents the charging and discharging power. So what we can see in the first graph is that the total net energy profiles show a boost in self-consumption, or a decrease in reverse power flow in the midday, which is achieved by charging the community battery and increasing consumption from prosumers. And in terms of local prices, it is obvious that the proposed local market always gives higher incentive than the conventional retailer because of the constraints in the formulation. So in the figure, you can see that the local prices are always constrained or within the range of the retail prices as we highlighted. And as you can see from hour 9 to 16, when this reverse power flow in the community, the aggregator decreased the buying prices to incentivize higher consumption in prosumers. And also within these periods, you can see that the prices in the 1 price scheme, which is the green line, is always lower than the buying prices in the 2 price scheme, which is the blue line. So basically, this means that the local prosumers can benefit more from the 1 price scheme. So in this slide, we quantify the utility gain of prosumers in both schemes. And what we can see from the figure is 2 things. 1. Prosumers always receive higher utility when participating in the proposed local market because of the positive utility gain. And also, the 1 price scheme provides them with higher payoff in all the simulated days. And that is the end of the case studies. So in conclusion, we've been able to propose a local market model with optimal community level battery storage. Specifically, we propose a local market model as a stackable game in which the aggregator is the leader and the prosumers are followers. The stackable game allows us to represent the strategic behaviors of the market entities since both the aggregator and the prosumers have their own interests. Next, we propose 2 business models for the aggregator, and we've shown that the aggregator earns 6 times higher in a 2 price scheme using real data of 33 prosumers, whereas in the 1 price scheme, prosumers always achieve higher utility in the chosen 36 days. And regardless of the pricing scheme, the payback period is always within the battery lifetime for the optimal battery capacity, which is roughly 6 Tesla Powerwalls. For the future works, firstly, we want to compare the financial benefits between the community storage and the household level battery units. The second work that we want to consider for the future is to make the user satisfaction function more practical by incorporating the cross elasticity of prosumers' responsiveness. And lastly, we want to consider long period battery sizing model to incorporate battery capacity degradation. And before I end my presentation, I would like to acknowledge the University of Adelaide and WAS Company in Denmark for sponsoring my PhD journey. I thank you for your time, and I'm happy to take any questions.